Hello, my name is Chris Edwards. I'm the UK and Ireland Sales Manager for ESPRIT CAM Limited. ESPRIT CAM is a full-spectrum CAM system offering high-performance programming of 2 to 5 axis milling machines, 2 to 22 axis turning machines, 2 to 5 axis wire EDM, and high-speed simultaneous 3, 4 and 5 axis machines. Also, we support Swiss turn, mill turn and B-axis multitasking machines. I would now like to introduce you to Paul Richards, who will be taking you through today's webinar on profit milling. Paul, it's over to you.
Hi Chris, yes, thank you very much for the introduction. Hello and welcome to this webinar on profit milling. I am going to show you different examples of profit milling in 2.5, 3, 4 and 5 axes. Profit milling is an optimized machining strategy that we offer in our full range of milling applications. My name is Paul Richards. I am a UK applications engineer working for DP Technology. If you have any questions at the end of this webinar, feel free to ask. I will start by explaining the fundamental principles of profit milling and then compare this with traditional milling and its limitations. Profit milling is an optimized machining strategy that allows the programmer to take significantly deeper, faster and more efficient cuts, whilst reducing wear on the cutting tool and machine. This unique patented method of optimized machining was developed to take into account the angle of engagement of the tool as well as the constant step over, rather than just one of these parameters. Profit milling manages the chip thickness formed during the machining of the material. The side cutting force in the calculation of the tool path is maintained by the engagement angle. This is the angular measurement of the edge of the cutting tool that is in contact with the material being removed within a specific range. It also incorporates dynamic feed rate changes throughout the toolpath and takes advantage of toolpath optimization such as machine acceleration and deceleration. Compare this to a traditional roughing cycle. Traditional roughing has its limitations, such as sharp corners and high engagement angles that significantly increase the width of the tool's cutting area. For example, the cutting tool can become fully engaged in the material along the first cutting pass or with sharp corner transitions. This causes the cutting tool to be overloaded, resulting in reduced tool life and in some cases, tool breakage. We have all experienced this by pushing the tool too hard. So we then have to adopt reduced feed rates along the entire tool path. The cutting depth generally needs to be reduced to avoid tool damage, normally 1 times D, but this depends on the material being machined, plus using smaller depths of cut wears out the bottom of the cutting tool. Traditional toolpaths calculate the feed rate based on the center line of the tool. When cutting in a linear tool direction, the feed rate at the cutting edge and center line are identical. With circular tool movement, however, this is not the case. The law of physics tells us that when milling in a circular path, the outside diameter of the cutter is moving at a rate different to that of the cutting tool's center line. These limitations force parts to be cut more slowly to account for these inconsistencies. Let me show you in this profit milling demonstration. Let's start by creating a pocket feature in our 2.5 axis example. Then we can select our feature and create a pocketing cycle. Let's select a 10mm end mill and change the tool motion pattern to concentric in. The incremental depth is 5mm and the total depth is 25mm. Let's change the surface speed to 180 and the feed per tooth to 0.075 for X, Y and Z. And the step over is 40%. We have a total cycle time of 5 minutes and 22 seconds. Let's run the simulation. Now let's change the standard milling cycle to a profit milling cycle. We can change the incremental depth to 25mm and change the surface speed to 300. And the feed per tooth is 0.279 for X, Y and Z. Let's change the engagement angle to 32 degrees. Let's validate. As you can see, now we have a total cycle time of 3 minutes and 2 seconds. Looking closely at the toolpath, you can see that we've got constant radial engagement. To make the profit milling even more efficient, let's change the step over to 10%. This has changed the cycle time to 2 minutes and 52 seconds. And the slotting and corner machining is more efficient with no slot movement or rest material. Now let's change the step down to constant. This is a bottom-up cycle, and this has reduced the total cycle time to 2 minutes and 2 seconds. After the simulation is finished, we can compare the NC code. As you can see, we have adaptive feed rate changes in the corners. Here we have a 3-axis example, and we're going to create a free-form feature. We're going to use conventional Z-level roughing. The surface speed is 250 and the incremental depth will be 0.45 with a step over of 80%. The depth calculation is adaptive. We have a total cycle time of 4 minutes and 30 seconds. Let's run the simulation. We're going to optimize the cycle by changing it to ProfitMilling and bottom-up machining. Changing the engagement angle to 40 degrees. Let's validate. We have a total cycle time now of 2 minutes and 19 seconds. Let's run the simulation. As you can see, we've saved a considerable amount of time by using ProfitMilling as the machining strategy. For our 4-axis example, this is machined on a turn mill machining center. We're going to create a freeform feature. From the very start, this is a ProfitMilling example. The tool we're going to use is a 16mm 3-flute end mill. The surface speed is 250 and the feed per tooth is 0.365. And we're using bottom-up machining. The incremental depth is 62 and we're using ProfitMilling. The engagement angle is 40 and the follow curve floor is yes. Change the axis start point to 20 and the axis endpoint to minus 170. And change the work offset transformation to RTCP. Let's validate. Let's run the simulation. As you can see, we are using the full flute length of the end mill to rough out and finish the part. That concludes the 4-axis example. For our 5-axis example, we need to untrim and extend a surface. We're going to hide our solid model and then extend the surfaces. We're going to use a linear extension of 20 millimeters on the one end and a parabolic extension of 100 millimeters on the other end. And then extend the other edges. We need to bring our solid model back. And then create our freeform feature. We can select Z-level roughing, select our 60 millimeter end mill. The surface speed is 350 and the feed per tooth is 0.45. We're using bottom-up machining and setting ProfitMilling as the strategy. The engagement angle is 50 degrees. And we need to select follow curve surface to yes and use our surface as a guide surface. We can show the toolpath using the Toolpath Analysis. Let's speed the simulation up. Now, when we run this on the machine simulation, you'll notice that the X-axis travel limit has been exceeded. So we need to change the machine. If you want to get in touch with us, the contact details are on the screen. Thank you for watching this demonstration of ProfitMilling in ESPRIT. I hope you enjoyed it. Do not forget to follow us on our social networks. See you soon for our next demonstration of ESPRIT.
To summarise today's session, all the strategies that you have seen Paul demonstrate today come as standard with the ESPRIT CAM. This means that all of our customers can take advantage of the productivity gains that Paul has shown you in this presentation. If you would like to see how ProfitMilling can help your business improve productivity by reducing machining time and improving cutting tool life, then please contact us using the links shown on this slide.